everyone, welcome to 11th hour. This video is going to be about the analysis of first order RL circuit. So let's begin by analyzing a source free RL circuit. So let's look at the circuit diagram. Here we have a resistor and an inductor connected in series with each other. We are going to assume that this inductor was initially connected to a voltage source and through a resistor, of course, because in one of the videos I showed you how after there is a steady uh, current flowing through the inductor, it acts like a short circuit, and therefore that would tend to damage the source or the supply. So we have an inductor here connected in series with a resistor, and say this is say 10 volts. Now this is going to charge. I'm not going to say charge. Now there is going to be some amount of voltage that is going to exist across this inductor, and that would be given by L di by dt, considering that I is the current flowing through this circuit. So we'll analyze this circuit a little later. Consider that initially we have connected the inductor to a source and there is some voltage existing across it. Then we disconnect it from this circuit and we connect just a resistor. So that's when we arrive at this. So we have removed the source and then it becomes a source free RL circuit. So we are going to consider that at t is equal to 0, the current that is going to be flowing through the inductor is going to be I of 0, which is going to be I naught. Because it was connected to the uh, source over here for a long time, and therefore, over a period of time, it got stabilized, and the steady state current turns out to be I naught. So now, once that happens, we have disconnected it and got the source free circuit. So now, once we connect this inductor to this resistor, and there is some I naught already flowing through this inductor, but since there is no source available, the magnitude of this current is going to decrease. So it is going to decay, and the decay will happen in an exponential manner. How is that? Why do I say so? So, when we analyze this circuit, we can form the KVL equation over here. Since I is the current flowing through this, initially the current was I naught at t is equal to 0, after which it was I. We need to find the expression for that I. For that, let's go with the KVL first. So, Ri plus L di by dt. So, that's the drop across the inductor, which is V, is equal to 0 because this is a source free circuit. So the solution to this is going to be I is equal to A e power st. So this is valid for t is greater than 0, isn't it? Now we can substitute this I in this equation, and what do we get? We get R A e power st plus L A. We have to differentiate this. So S e power st, this is equal to 0. So on simplifying, we get A R plus Ls e power st is equal to 0. Then what is S over here? So we can say that R plus Ls is equal to 0. Therefore, S is equal to minus R by L. So in the expression I is equal to A e power st, we have been able to find the value of S. Now we need to find out what is A so that we can find out the current flowing through a source free RL circuit, the expression for it, right? So we are going to use the initial condition that I of 0 is equal to I naught. So when t is equal to 0, I of 0 is going to be I naught, or I is going to be I naught, and A e power minus R by L, and t is equal to 0. So e power 0 is nothing but 1. So I can say that A is equal to I naught. So from this, we can establish that I of t for a source free RL circuit is going to be I naught e power minus R by L t. So now for a source free RL circuit, I of t is I naught e power minus R by L t. Here, the time constant for this circuit given by tau is going to be L by R. Let us now consider the case where we are going to connect the inductor through a resistor to the voltage source and then find out what is the DC current that would be flowing over a period of time when the circuit attains stability. So here at t is equal to 0, this switch is closed. Therefore, there would be current flowing through this circuit in this manner. So that current would have two components. The first component would be the homogeneous component and the second one would be the particular solution. Why do I say so? So let's form the KVL equation in this loop and find out why. So when there is this current I of t flowing, R I of t plus L d I of t by dt is equal to V naught. This is going to be my KVL equation for this particular loop. Now this is a linear differential equation, so it will have two solutions. So therefore I of t would be made up of the homogeneous solution and the particular solution. This is going to be the natural response and this one is going to be the forced response. So the homogeneous or the natural response is going to be given as A e power minus R by L t. And the forced response is going to be given as V naught by R. So this is going to be the forced current in this inductor. This is occurring because the value of the source is V naught and there is a resistance R in the circuit, forcing the current IP of t being equal to V naught by R. This IH of t is the natural response of this inductor, and in order to find the value of A, we need to apply the boundary conditions or the initial conditions. So here at t is equal to 0, the I of t is actually 0. We are not considering that it was connected to a source before this and all. So this is that case. What is going to happen when we connect the inductor to the source? So before this, there is no current that was already flowing through it. So it was not connected to any other part of the circuit before this. So I of t when t is equal to 0 is going to be 0. So applying this to my I of t, I would get I of 0 is equal to A e power minus 0 plus V naught by R. So here, when we simplify this, this being 0, what we get is e power minus 0 is going to be 1. So A is going to be minus V naught by R. So let us now apply this condition to the I of t and find the final equation for this current. I of t is therefore going to be equal to minus V naught by R e power minus R by L t plus V naught by R. So on simplifying, we'll get V naught by R 1 minus e power minus R by L into t. So this is going to be my I of t. So the heading says establishing a DC current. But right now we saw that I of t is equal to V naught by R 1 minus e power minus R by L t. So where is the DC current over here? You might wonder, right? So if I leave the circuit in this manner with the switch closed for a long time, then there is going to be steady state current flowing through the inductor to the extent that this inductor would act like a short circuit, because if there is going to be a V across the inductor, that would be given as L di by dt. But over a period of time, after the circuit has settled, I would become consistent. So there won't be any change in current. So L di by dt would be zero. So the voltage across this inductor would be zero, meaning short circuit. So the circuit would essentially be looking like V naught with the resistor. That's all. The inductor would be as good as a short circuit in this manner. So in that case, what is the current that would be flowing through this? So then it would be V naught by R. That is the forced response. That is the current that would be flowing through this arm or this branch where the inductor is going to be connected. Now, what is the voltage expression? So V of t is L di by dt as mentioned. So I need to differentiate this so that I get the expression. And what do I get? I get V naught by R into L 0 R by L. So there would be a minus sign here, and the minus sign from this exponential, both will make it plus e power minus R by L into t. Now this L and R cancel out, and I get V naught e power minus R by L into t, where the time constant tau is L by R. So these are the two important expressions in case of a series RL circuit. One is I of t is equal to V naught by R 1 minus e power minus R by LT. The other is the voltage. V of t is V naught e power minus R by L into t. So looking at the expressions, we can actually guess the shape of the response, the time domain response of this RL circuit. So if we look at the current, right, when it is connected to the voltage source, the current actually would be rising exponentially, where the expression would be I of t is V naught by R 1 minus e power minus R by LT. Here, L by R is going to be the time constant, and V of t is going to be equal to V naught e power minus R by L into t. So that's why the shape of these two curves appear in this manner. Here, if I replace t with the time constant, so when t is equal to L by R or the time constant, in that case, the value of I of t would be 0.632 into V naught by R, because this would become e power minus 1, and 1 minus e power minus 1 is 0.632. So if we look at the voltage response, it starts with V naught and it decays till the steady state current is attained at the inductor, and the inductor acts like a short circuit, and therefore the voltage across it decays down to almost zero. And here, when the t is equal to L by R, when we replace that value here, we'll get V naught into e power minus 1, which is V naught into 0.368. So this is the time domain VI curve of the RL circuit. Let's look at this simple numerical example. So here we've been asked to find I of t and V of t of the inductor for all times. So let's split it as three periods. One is when t is less than 0, at t is equal to 0, and for t greater than 0. So we see that in this circuit, this switch S was closed for t less than 0, and it was opened at t is equal to 0. So the voltage source and the resistor got disconnected at t is equal to 0. After which, that is for t greater than 0, the inductor and only the 10 ohm resistor would be connected. Because since this switch is opened, there won't be any path for the current to flow through, and therefore only the zero point 0.1 Henry inductor and the 10 ohms would be connected with each other. So let's analyze this step by step. So for t less than 0, we can assume that the 12 volt was connected to this inductor for a long period of time. So we can simplify this circuit and say that it is going to appear like this. The switch is closed, so there is this 4 ohms, and over a long period of time there would be steady state current in the inductor, so therefore the inductor would act like a short circuit, and this 10 ohms is going to be there. But since there is a short circuit in parallel with this 10 ohms, the current is going to take the least resistance path, and therefore no current will flow through the 10 ohms, so we might as well remove it. So this is going to be the circuit with the 12 volt source and the 4 ohms connected in series with each other. Therefore, what is the current which is going to flow? It is just going to be 12 by 4 amps, which is 3 amps. So we see that the short circuit current, that or the steady state current for this inductor, or I naught, is going to be 3 amps. Now at t is equal to 0, this switch has got disconnected. Therefore, this part of the circuit is not going to be connected to the inductor. So therefore now the circuit is going to boil down to just the inductor connected with the 10 ohms. And now this is going to act like a source free RL circuit. So this is zero point 0.1 Henry and this is 10 ohms. So we need to find out what is I of t and V of t. So I of t for a source free circuit we know is I naught e power minus R by L into t. And V of t is equal to V naught e power minus R by L into t with the negative sign over here. Now let's compute what is R by L. So we'll have R is actually 10 ohms over here, L is zero point 0.1, and I naught we've obtained it as 3 amps. So we can replace these values, 3 e power minus 10 by 0.1 t. So now we can obtain I of t as 3 e power minus 100 t amps. On the other hand, what is V of t? V of t would be equal to 3 into minus 100, because we can obtain it as L di by dt. So 3 e power minus 100 t is going to get differentiated and multiplied with zero point 0.1. So I'll get 3 into minus 100 e power of minus 100 t into L. L's value is zero point 0.1 Henry. So this is going to be minus 30 e power minus 100 t volts. So I hope this is clear. This is just L di by dt, where uh, I have got the I of t as 3 e power minus 100 t. And the value of L here is zero point 0.1 Henry. So this is how we can analyze and simplify any RL, first order RL circuit. So that's all with today's video. In the upcoming videos, we look at complex RLRC circuits and numericals related to it and how to approach these problems. Please do subscribe to this channel, and thanks for watching.